5 and 11. This is using the perfect square, perfect cube method. So if you want to see the other method, let me know. So the highest perfect square that we can divide 512 by is 256. Square root of 256 is 16. And then 256 and 2 are the two numbers. And then 2 goes into 9 8 times. Nope, that was wrong. 2 goes into 9 4 times, which would be 8 with 1 left over. 2 goes into 4 twice with 1 left over. And then 2 goes into 10 5 times with nothing left over. Nothing left over for the q's also. So then 16p to the 4th q squared r to the 5th times the square root of 2p is your final answer. There's a lot of variables going on there. Questions on that one? Do we need to say it the other way? Did you happen to do this one the other way? Yes. Can you give me the two factors you use? That's okay. I think a lot of you use 64 and 8. Yeah. So we could break 64 down to a bunch of things. So let's just do 8 and 8. So we have 4 and 2, 2 and 2, 4 and 2 and 2, and 4 and 2 and 2. Bunch of 2s all over the place. So pairs, we have 1, 2, 3, 4. I'm missing something. Oh, this 2 would be by itself. Okay. So on the outside we have 2 times 2 times 2 times 2 with our lonely 2 on the inside. P's, R's, and Q's, if you listed them all out, you would find that we have 4 pairs of P's, 2 pairs of Q's, and 5 pairs of R's, but I'll do that real fast. And I did too many P's. Okay, so 1, 2, 3, 4. I'm just going 1, 2, 3, 4, 5, 6, 7, 8. It was 9. Got it. I erased too many. So 1 P left over. 2 pairs of Q's, 5 pairs of R's. So you would write that out. 4 P's, 2 Q's, and 5 R's. With P on the outside, inside. So if we simplify all of that, we have 2 times 2 is 4, times 2 is 8, times 2 is 16. P to the 4th. Q squared, R to the 5th, and on the inside, 2 and Q. Other questions on that one? $11. I didn't really see this in this class, so for you guys, I saw this more in second period where we thought this was 10 to the 3rd and not the cube root of. So make sure you keep that separate. Draw in parentheses if you need to. They did this a little different because I want you to take out the negative first, so you have negative 10 and then the rest of that. They're doing perfect cube method, so the highest numbers would be 8 and 3. And then 3 goes into 8 twice, which would give us 6, and there'd be 2 left over. 3 does not go into 2 at all, so b squared would stay inside. And then negative 20a squared times the cube root of 3a squared b squared would be your final answer. Anyone have questions on that? Want to see it done the other way? Okay, go ahead. And then we're going to go over the 2 on the quick check. I know some of you were doing that, some of you were doing this, so if you didn't get to that, that's okay. Let me know when you're done writing. I would say if you didn't get this, write down the answer, but still try it out yourself in the way that you are most comfortable with. Because if you're not comfortable with this way, you should be practicing the other way. Nature.
This one, so would be a to the 8 over 3. A to the
Yeah. So don't get too caught up on that notation. So as you're doing this method using that rule, they're saying we're dividing by 3, and 3 goes into 8 only twice. So then we're multiplying that 2 and the 3 together to get the 6. And then we're looking at how much is left. From 8 to 6, there'd be 2 left. And then simplify this one. This was supposed to be 3, not 3, So this one would be inside, this one would be outside. But as long as you know that 3 goes into 8 twice, and there'd be 2 left over, as long as you can do this part, don't worry too much about this notation. Don't get caught up on that notation. Nature.
How do you end up with a 6 power?
24 is 8 and 3. So the way they broke this up is not the way we would break it up. We would break it up by number and then variable. They were doing something different. They broke it up by all the perfect cubes all in one, and then like that, disregard that part. Do what makes sense to you. This is not my handwriting. This is just an answer key that has a. So we would do it like, bring the negative out, and then we'd say the cube root of 8, the cube root of 3. 3 goes into 8 twice with 2 left over. 3 doesn't go into 2, so that would just be the cube root of b squared, and then rearrange. Disregard this part. Don't focus on that part. Other questions on that one? So you were supposed to do 2 and 3 if you weren't doing 5 and 11. Anyone get 2 that they want to share their answer for it? Answer and work. Alright, so if we're doing this, do we want to use perfect square or factor tree method? Anyone? Okay. So give me 2 factors of 196. 14 and 14. What that really means is 196 is a perfect square, so we could have just brought that down, but since we're doing factor trees, we're going to bring it down all the way. I don't know why I said it like that anyway. So we have a 7 and a 2 that comes out. If we're doing factor tree method for our variables, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And we're looking for pairs. We have a pair of x's with 1 left over, 2 pairs of y's, 4 pairs of z's with 1 left over, so that would look something like 1 pair of x's with 1 that stays in, 2 pairs of y's with nothing left in, 4 pairs of z's with 1 left in. Then we can put all of the outside pieces together. We have 7, 2, x, y squared, z to the 4th. Put all your inside pieces together, which would be x and z. And then simplify it. 14xy squared, z to the 4th, times the square root of x is z. Questions about that one? Emo?
Can you write a 1 on top of them? Yeah.
Sure. So you could put a 1 here, 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 here. All your numbers and variables that are by itself has an exponent of 1. That would not be incorrect. Now when we get into exponents, I wouldn't want you to put that 1, but for now, you can. Other questions on that one? Number 3. Was this answer correct? Anyone figure that one out? Was that answer correct? No. No. They were close. So if we were to do this, I'm going to do perfect square method for this one since we did factor 2 for the other one. Think about your perfect squares. Try to think about this without using your calculator. Highest perfect square we can divide 162 by. So if we're thinking about our perfect squares, the one underneath this would be 1, 44, so that would be too close. 121 would still be too close. It's going to give us decimals. 100 is not divisible by 100. 81 seems like it. Is it 81? Okay. Yeah. As I say, 81 it might be. Usually these are like whatever it is and 2. That and 2 will be your perfect square, perfect cube, whatever. So 81 and 2. And you could double check that. Multiply off to the side. 81 times 2, would you get 162? Yeah. So this would give us 9. And then our variables. This 5 is not connected to the square root. Our index is still 2. 2 goes into 3 how many times? Does it go in twice? Once. So as long as you know that 2 goes into 3 once, and how much would be left over? 1. As long as you know that, don't worry about the notation. But if the notation helps you, you can still do it. The notation would be me dividing 3 and 2 together, me realizing that 2 only goes into 3 once, and for it to go in once, I'd have to multiply whatever number I just said, that 1, by whatever the index is, which is 2, and see how much I would still need to get whatever I started with, which is 1. That 1 by itself would still be inside. So when you simplify this, you have to know that this one's your inside and this one's your outside. Pretend those are total brackets. So as long as you know that, whether you do this notation or go straight into this, does not matter. So don't get too caught up on that part. 2 goes into 2 how many times? Once, with what left over? Nothing. So we have on the outside negative 4a to the 5th times our 9 times the square root of 2 times a times the square root of a times b. And then I'll rearrange. Negative 4a to the 5th times 9 times a times b. Some of those look like all the same thing. This one is a 9. I don't know if I made that better or worse. So we can multiply the numbers together. We haven't talked about exponent rules yet, but anytime we have multiples of the same variable, you're really just adding the exponents. So this would become a to the 6. These are all a's. So the person was close. I think they forgot to multiply negative 4 out front, and whatever they simplified by got the 3 instead of 9. So something they did was off there. Questions on that one? Major.
Sorry, I don't have a question. Can we go to
Yeah. Did you fill out that you'll help us already? Okay. So the next thing we're going to do is like taking what we've already been doing and going up a notch with it. My brain is like not good. There you go. Okay, so when we're doing this, think about these kind of like when we combine like terms. When we combine like terms, they have to have the same variable, same exponent in order to combine them. Similar, but different. For this, in order to combine radicals, add them, subtract them together, they both have to have the same index, so they both have to be square root, cube root. I can't add a cube root and a square root together. But they also have to have the same radicand, the number underneath the radical. So if these are the same, and these are both the same index, so these are both square root, they both have a radicand of 6, then just like when we combine like terms, we really just take the number in front, add or subtract those together, and then put x at the end. Same thing. So this would be me adding or subtracting 3 minus 2, which would give us 1. And then I would just put the radical afterwards. Or just radical 6. The other part to this is we have to make sure it's completely simplified. If I were to break down 6, what numbers would I get? 3 and 2. Those do not make a pair, so this is as simplified as it's going to get. I cannot break down the square root of 6 anymore. So this would be my answer. What questions do we have so far? Really?
So the only thing that, like if we subtract or adding is the thing outside of the radical?
Yes, but you may also need to simplify what's inside. So we'll get to that in a second. So then if I said simplify number 2, or combine like terms, if you think about it like that, what would your answer be? 4 times the square root of 5, or you can say 4 root 5, either or. So you're just taking the numbers on the outside, adding those together, putting the square root, if they're the same. 5 can't be simplified because it's prime. So if it's prime or the breakdown would still be prime and doesn't have any pairs, it can stay. So starting to recognize some of those will help you realize, do I need to simplify this more, or is it good? But like number 3, Right now, we cannot add these together because they don't have the same radicand, the number underneath. But can 63 be simplified? Yes, to 9 and 7. So if we're doing factor tree method, break it down all the way. So we have a pair of 3s that's going to come out. Bring down everything else. So 10 times the square root of 7 plus, we're multiplying this by 2, and the 3 came out. The 7 would stay in. Multiply to get what? 6 times the square root of 7, and then simplify. 16 times the square root of 7. Okay. Questions so far? Then sometimes we get something like 4, where we may have to simplify them both. Just like with combining like terms, when you combine x's, if there's nothing in front of an x, that's a 1. You don't see anything in front of a radical, assume that is also 1. Right. If we break down 15, what numbers would you get? 3 and 5. Neither of those are pairs. So that would stay just 15 because it can't be broken down further. So 15, 6, those are both things you can break down, but that you wouldn't be able to take out a pair. So those are as simplified as possible. We can break down 60. So let's do this using perfect square since we just did factor tree. What is the highest perfect square we can divide 60 by? Really? 10 perfect square. That would work with factor tree, but it wouldn't work for the perfect square method. Think about your perfect squares under 60. 49 is too close. 36 times 2 is 72, so that wouldn't work. 25 times 2 is 50, so that wouldn't work. 16 is close, but 16 times 2 is 32. 16 times 3 is 48. Times 4 is 64. That would go over. Given 4. Sometimes the highest is not very high at all. So we have 4 and 15. We already found out that 15 cannot be simplified anymore. But we know this would be 2. Bring down your root 15. Oh, I forgot the 6. And the negative 6. Multiply and simplify. What would we get? What do we get for that one? That would be the answer for this one, but if we're subtracting, and this is 1, Cameron? You were close. But if we forget that that 1 by itself has a 1, and we don't combine those, we're going to end up with a wrong answer. What questions do we have so far? We're going to jump to the next page. So if you get something like 14 where right now we cannot combine any of these because they don't have the same radical, we need to see what can we simplify from here. We already know from the previous problem that the square root of 6 cannot be simplified any further, so we don't need to worry about that part. We can skip to the next one. If you want to do one part of this by perfect squares and another part by factor tree, you can do that. If you want to do it all by factor tree, you can do that, or all by perfect squares, you can do that. I will say, some of these, you'll get a lot of numbers. So if you need extra space, use scrap paper. Don't try to bunch your entire answer in here if you can avoid it. So I'm going to use perfect square for 150 and then factor tree for 54. What is the highest perfect square we can divide 150 by? $75 a perfect square. Factor tree, that would work. Cameron? 25 and 6. So that would give us 5 times 6. And then our 18 in the front. I'm going to also bring down the 10 root 6, or 10 times the square root of 6 in the beginning. Now if we're doing factor tree, give me two factors of 54. 6 and 9. We have 3 and 2, and 3 and 3. We have a pair of 3s. So that pair of 3s would come out, so this would be negative 4 times 3 times the square root of 3 times 2. So I'm going to simplify that first, and then we'll see what we can combine. I'm going to write this up here. 10 times the square root of 6 plus, this would become 90? Question mark? I'm pretty sure it's 90, but you can double check that. And then minus 12 times the square root of 6. Combine your like terms. Tell me what you get. You said 80. 88 times the square root of 6 will be your final answer. Because all of these can be combined. So sometimes you'll end up with one term answer, sometimes you'll end up with 2, 3, 4. It depends on how many you start with, how many are like terms at the end. Sometimes you could get 4 different radicans, whatever, and they all not be the same. So it really just depends. Okay, before I let you pick any that you want to see go over, have questions about, I want you to look at 17. We're not going to actually do it unless that's one of the ones you want to see. What does perimeter mean? What do you do to find perimeter? Add up all the sides. So if you get something like this, it says, what is the perimeter of whatever shape? Don't let that confuse you. You're still doing the same thing. You'd be adding up all of these, simplifying each thing, finding the like terms at the end, and going forth with that. I will say for 18, it doesn't give you a shape, but it still says find the perimeter. It's talking about a rectangle. So if you need to draw a rectangle, put in your numbers. But remember that rectangle has 4 sides, not 2, and they only gave you 2. So remember that these should be there twice. So you can either add them up, this plus this plus this plus this, or remember that the perimeter of a rectangle is 2 times your length plus 2 times your width. Either or. As long as you're adding up all the sides, you're good. Look at numbers 5 through 18. Of those, which ones do you see that you have questions about? You're not sure how to start. Maybe you started, want to check that you're right. you're not sure about, you're confused about, anything like that. Lily. 15's nice. Because can we simplify 5 or 7? No, those are prime numbers. So if we can't simplify anything else, we're just looking for like terms and we just have to combine. So here we have 3 things that are like terms. If you don't have a like term, you would just bring that down. So if we combine these, what would we get? Nature. 4 times the square root of 5, then we would just bring down the plus 3 times the square root of 7. And that would be your answer. We can't combine those. They're not like terms. There's nothing else we can do with it. It also does not matter the order in which you put it. If you wanted to do 3 times the square root of 7 minus 4 times the square root of 5, you could do that. Both are right. As long as the signs are in the right places. Questions about that one? Or other questions 1 through 18? 5 through 18. We did 1 through 4. Here. So Josephine. 16. Of these numbers, which ones can we simplify? 8. So let's say we were doing perfect square. What is the highest perfect square we can divide 8 by? I heard it, but you said it like 4. So this would be 2 times the square root of 2 times the 4 that was already there, and then bring everything else down. So then we would multiply and simplify. Do that. Multiply and then simplify. Tell me what you get. What did we get there? Nature, go ahead. Who else got that? Couple of us. Does anyone have questions about that one? Mm-hmm. So we multiply the 4 and the 2 together to get 8. And then the like terms you see would be these two. Combine them. -3 minus 5 will give us the -8. We just put the -6, square root of 6. And then the 8 plus the 4 we get the 12. Other questions on that one? Any others? 5 through 18. Nature. Mm-hmm. So perimeter, we know we're adding, so we're going to be adding these 3 together. The order in which you put them does not matter. Of the radicals, which ones can we simplify? 72 and 18. So we're going to have to simplify both of those. Sometimes you'll have to simplify everything. Sometimes you'll only simplify one thing. Depends. So I'm going to do perfect square for 72, and then we can do factor tree for 18, or you could do 1 for both, doesn't matter. Highest perfect square, we can divide 72 by Ava. 36 and 2. So this would give us 6 times the square root of 2 with the 2 out front. Give me 2 factors of 18. Ava, go. 6 and 3. Which will give us 3 and 2. We have a pair of 3s that would come out. So this would be plus 8 times 3 times the square root of 2. And then we would bring down our 16 root 2. Then we would multiply and simplify. Do that and tell me what you get. Times the square root of 2 should have been your final answer. Anyone have questions on that one? So, from the beginning or just from here? So this would be 12 times the square root of 2. This would be plus 24 times the square root of 2, and then the 16 is already there. Then add 12, 24, and 16, and you should get 32. Okay, we're going to switch gears and go from adding, subtracting to multiplying, where the rules change a little bit. So before adding and subtracting, they had to have the same radicand in order to combine them. Now that doesn't matter. Kind of like with fractions, when you multiply fractions, you do everything, but when you add and subtract fractions, you only do like the numerator. So here, what you do is you take the outside pieces, multiply them together. So for number 1, there's 1 here, so it'd be multiplying 1 and negative 3. And then we'd be multiplying the inside pieces together. Everything that's inside the radical, but I'm going to put them both inside one radical. And then multiply and see if we can simplify. So this would become negative 3 times 16. Can we simplify the square root of 16? Yes, to what? 4. And then we would just simplify that. Sometimes these will get whole numbers, sometimes they won't. It really depends on if we got perfect squares, perfect cubes, or not. Questions on that one before we do another? Multiplying the negative 3 from the outside, and then the square root of 16 is 4. Multiplying those. For number 3, I'm going to skip around. Again, multiplying your outsides together, multiplying your insides together. So we get negative 35 times the square root of 120. Can the square root of 120 be simplified more? Yes. So let's do factor tree. Give me two factors of 120. 12 and 10. If that's not what you chose, you can pick two others. That's fine. We have 6 and 2, 6, and 5 and 2, and 3 and 2. So we have a group of 2's, and that's it. So on the outside, we have negative 35 times 2. On the inside, we have 3 times 5 times 2. So this is negative 35 times 2, and then 3 times 5 times 2. So negative 70, and on the inside, 30. It looks like we should simplify that more, but as we just saw, these would be the prime numbers it breaks down to. None of those are pairs, so the square root of 30 is another thing that cannot be simplified more. It would just stay as is. So negative 70 times the square root of 30 would be our final answer for that one. Questions on that? Do one of these ones with variables. 7. So same process. I'm going to start to multiply a little bit faster without putting everything. So on the outside we have 2 and 1. So 2 times 1 would give us 2. On the inside we have 15 times 3, which would give us 45. And then I'm going to write out the variables and then explain what we're doing with them. But normally I would just put the next answer. So again, this is not something we've really formally talked about yet. But if you are multiplying the same variable, you're adding these exponents. So this is going to become just w to the 7th. Can we simplify the square root of 45 times w to the 7th more? Yes. Perfect square or factor tree? Perfect square. What is the highest perfect square we can divide 45 by? 9. So that would give us 3. Let me write this over here. And then 2 goes into 7 how many times? You close? 3. So the w to the 3rd with how much left over? 1. Okay, so things on the outside, 2 times 3 times w to the 3rd would be 6 w to the 3rd. Things on the inside, 5 and w. Questions on that? I want to do at least 3 more seconds, but I don't know if I'll have time to draw there. This one, be careful with this one because there are 2 different things going on, multiplication and addition. The addition thing, we can't do anything unless they have the same radicand. So you will have to see if you can multiply this, simplify it, and then see if we can add or subtract. So if we multiply these, this would just get brought down. This, all on the inside, would become 12 times 2 would be 24. What would my x's become? to the 6. Then from there, you would see, can we simplify that more? If we did perfect square method, 4 and 6 would work. 2 goes into 6 how many times? 3. With nothing left over. So we have 7x to the 3rd root 6 plus 2x to the 3rd root 6. Now do we have like terms? Yes, they have the same variable, the same exponent, the same radicand. All of that has to apply in order to combine them. If one had x squared and one had x to the 3rd, we could not add them. The same variable, same exponent, same radicand. Okay, do we have questions about that one? There's like one more, Iman. Yeah. There's like one more piece of multiplying that we have to talk about that looks different than this. Same thing though. On the very last page or the next page, I don't remember. You may see multiplication problems like this where you're distributing. Think about just distributing normally. We multiply whatever's outside to everything inside. Same thing. So here we would multiply these two and multiply these two.
So it's pretty much the actual number, like the number that the square root equals to.
Yes, I know. Because here we're still multiplying the outside number. So this would be 1 times 3 times the square root of 6. So you would still have to put both. And then here we're actually multiplying the square roots. Underneath one radical. So then multiply that to get what? And then simplify. So whether you use perfect square method or factor tree method, put mostly. If I did perfect square, we'd use 16 and 3, or you could break it down, find your perfect pairs, just pairs. Can we combine either of those? No, they're not like terms. Because we have a radicand of 6 and a radicand of 3. And that would be your answer. Questions on that before I show you this last one, and then I'll let you practice one, and then we'll be done. It's been a long class. This second example is distributing twice. So you may have seen that before, you may have not.
So for when we're distributing it, we're multiplying it by one. If there's no variable, like number in front of the
Like right here. Yeah. There's a 1 right here. That's what we multiplied 1 and 3 by. For this one, I would rewrite it so that, I don't know if this is going to look better or worse, but we're taking this 4, multiplying it to everything here. So 4 times this second set of parentheses. And then we're taking this second term and multiplying it to that second set of parentheses as well. So we're distributing twice. Then you would take whatever's outside, multiply it to everything inside. So this would give us 8 minus, I'm just multiplying what's outside here since this is not a radical, so 4 times 1. And then here, same thing, I'm multiplying what's on the outside to 2 since this is not a radical, so 1 times 2. But here, I'm multiplying the radicals together underneath the radical. So we have to keep track of what numbers we're multiplying and where. Outside things together, inside things together. Inside the radical together, outside the radical together. Can the square root of 9 be simplified? Yes, to what? 3, because it's a perfect square. What terms could we combine from this? Square root 3's we could combine together. Anything else we could combine together? Eight -3, because we simplify them. Okay, so what would that be when we simplify it? Look at just your like terms, combine just those like terms. Nature. 5 minus 2 times the square root of 3. Usually in these type of situations, you want to put that number by itself in the front, otherwise it kind of gets lost in the back. Or we add it underneath the radical and we don't mean to. Do we have questions about that one? This is a challenging one, but I want you to try this. Number 14. Remember what's outside, remember what's inside, those things go together